So today we'll be talking about, or in the next 2 hours, we'll be talking about pthreads. There are, as I already mentioned, some exercises, the slide deck, and some code snippets on the homepage. And we'll be talking about a bit of shared memory, where I assume that since you've already had some Python threading exercises yesterday and some MPI exercises yesterday, that this is just kind of a repetition to get started today, and afterwards we'll be talking about POSIX threads. So after this course today, you should be able to compile and run a pthread program. You should know how to spawn the threads, and you should actually know how to handle a critical section and know what a critical section is. For this, because this is a practical course, we'll be spending a lot of time actually with the exercises in the breakout rooms, and not so much time in the broadcast room with a lot of slides. However, whenever you have questions, please don't hesitate to either ask here or to write into the chat, or however you want to get in touch with me or the others that are here to help. Okay, so first of all, let's talk about a bit of shared memory. What is shared memory? Well, you're going to have several cores, several processes actually using the same bit of memory. So this also means that you have to do all the communication and coordination through the memory. Yesterday you talked a lot about MPI. There you had the explicit communication and message passing. Within shared memory, this is going to be a bit different because you all have access to the same variables. And just to kind of get you talking and get started a bit, we're going to start with a small breakout session, and you go ahead, find your rooms, talk about what needs to be kept in mind in shared memory programming, and get everything set up. That's why we're taking 10 minutes for this breakout session. And we'll be back here at 9:17, please. So recording started again. Let me first skip to the next slide. So yes, you pretty much mentioned everything, maybe in different words, but we have deadlocks to take care about. We have data races to take care about. We have to look at the timing of the threads, meaning which thread does what at what point in time. And we need to take care of access control and variables. So the access control and variables is pretty much what you do over synchronization, over access control variables we will be talking, or access control mechanisms we will be talking about within this lecture, and that you'll actually be using. And the other thing is the word communication, which I always find somewhat misleading in shared memory programming, because you have access to the same variables, to the complete data that every other thread accesses. So why should there be need for explicit communication? So it's more kind of an implicit communication that you have, if that makes sense for you. So now, how does pthreads actually help us with that? POSIX threads are a standard for Unix-like operating systems. This means that they are on Linux, Mac OS, Solaris, and other Unix-like systems, but you don't have them on Microsoft systems, at least not natively. So it's a library that you have to link to your C programs, and this would be actually one question which is important for the exercises afterwards. I hope you all know basics of C programming. If you have any questions on that, do not hesitate to ask at any point in time. POSIX threads are very low level, as C already is kind of low level. It's not one of the very fancy, user-friendly kind of interfaces. The same is true for pthreads, which also means that you have a very low overhead. And what the pthreads header or the pthreads library gives you is certain functions to explicitly control the access to certain variables to actually spawn different threads and make them work for you. So as we are talking about a library, you're going to have to include the source file always, and you'll also have to link the library afterwards when compiling. Afterwards, you can run it as any other program. In this case, you already see here, we're going to be handing over the number of threads to be used to the program over the command line. Just keep this in mind, but this is also described on the exercise sheets whenever you need to talk or whenever you need to do run and compile something. So what's this thing with spawning or forking and joining threads? So you start your program with one master thread. And at some point in time, you say, okay, I have a huge array. It doesn't make sense for one thread to work on all of this. Let's have some threads working on the array consecutive at the same time in parallel. For that, you spawn more threads from the master thread. And after they have done their work, you have to join them again. So this is kind of a small synchronization that you have at that point. Now, for creating threads, you're going to need thread handles. Hand that over as an array, as a pointer, and you're going to need a function to be defined which the threaded or the threads are actually going to work on afterwards. And afterwards, as I said, once they return out of the function, you have to join them again. But I hope that this principle is clear after all the experience you gathered yesterday. So nonetheless, let's look at this a bit closer. We have a Hello World program, as we always do. And I would like you to just have a look at the source code, look at the thread function, look at how you actually move the data around, how you access to the data. Have a really close look at the variable's thread count. And then I would like you to do your first compiling and running of the program. You can either run or do the exercises on your own system, or you can do it on the cluster as you wish. Any questions on that? Okay, so then we have 10 minutes for that, which means we're back here at 9:35. And I'll be coming around the rooms a bit to just see how you're doing, whether you have any questions. Okay, so we're back from the breakout sessions and we've collected some answers in the chat. I will be going through those. But more or less there are also right here. So the value is defined over the command line. That's how you get to the value of thread count. And it's stored in the global variable thread count. So this is what I was just starting to talk about, a global variable versus private variables. What's the scope of the different variables? You see in the source code, it's the value thread count is defined outside of all of the functions. So this is going to be a variable that is shared among all functions, that is usable by all functions and also all threads. Meaning all threads can use and alter it. And the other variables you have, they're defined within the functions. They have a private scope, a more private scope, especially those within the threaded function. Only the thread that starts the function can actually use the variables within the threaded function. Good. The second question, actually, no one has answered within the chat here, but when I walked through the groups, I already saw that you saw what happens, namely the print statements are printed out in different orders. So this is something we have to keep in mind, that I hope you ran it a couple of times so that you also see that the order is different from the time, from each time that you run it, or it can be different. And this is non-deterministic. And this is something you really have to keep in mind when writing a threaded program. You do not know in which order a thread accesses the threaded function. Do you have any questions on this part, or is everything clear so far? So no one starts typing or is speaking up? Oh, someone started typing. All clear. Good. So let's resume. The estimation of pi is an example that you already had in MPI. I hope you recall what you did there. If you do not, here's the single-threaded code. And I would like you to just have a look at it and then think about what steps you need to take to parallelize the code snippet with pthreads. If you're really quick with that, you can go ahead and start with the next question as well, but feel free to take the 10 minutes in the breakout room to just really discuss what steps you need to take to parallelize it. So again, it's 10 minutes, so we're back here at 9:51. So before I get back to this question from the breakout session, I want to get back to one comment that I saw in the chat just now. So someone said the threads are created by allocating memories for the handles. This is not quite correct. You create the handles, or you make space for the handles, but you do not actually create the threads. The threads are created and forked with the corresponding pthreads function. So just to clarify that one. Then getting back to the estimation of pi and what steps you need to take to parallelize the above code snippet. So let's get back to the code snippet and talk about it. So we have three answers, or three people answering that we need 3 steps. And those steps could be creating some threads, splitting the sum to the threads, and collecting the sum and threads and the results. So this means you would add some code, probably somewhere around here, where you create the threads, and you would actually want to split this sum. So you would do that within the function, or how would you do that? While I hope that someone answers, I would continue with collect and sum the results. So that would probably happen somewhere here. So no further explanations on splitting the sum to the threads. Oh, now she's typing. So anyone think that we need more than 3 steps, or is everyone fine with those 3 steps? Okay, so to split the sum to the threads, we could make another function that takes the lower and upper limits for the sum, okay? So this is actually one step that's quite important. You need to take care of where does each thread start with summing and where does it end with summing up. And there's still a lot of typing going on. Okay, so one person thinks we don't have to collect if we have a global summation. Yes and no. So you're going to have some local sums you do make and then sum it up globally, but you also could, so it kind of depends on what your plans are on parallelizing it. Okay, the steps are more meta steps. When we code, we might need more changes. And housekeeping steps, exactly, like including stuff, the global variables. Those are all things that we have to talk about. So yes, if you say it's more meta steps and we might need more changes, this is exactly something that I wanted you to talk about or to think about, because actually it looks like that. So you're going to have 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, 12, 13 steps is what I collected by really tracking the changes that you do to this code when parallelizing it. So there's quite a lot you have to think about. And it starts with little things like adding a pthreads header or with things like getting the number of threads and end from the command line, having global variables, make sure that you have the thread handle, create the threads. What do you have to think about in the threaded sum function? Because no one actually talked about creating this threaded sum function. And what does this function do? What is it supposed to do? What resources does it need? So what do I actually need to make a global variable? And afterwards, you have to join those threads again, free everything, clean up, and also calculate the final estimation of P within the master thread. With this, I mean this part here. This should be done after you have joined the threads. I hope it's clear to everyone why. And now having these 13 steps in front of you, do you have any questions on those? Because if not, I would like to give you this, how should I call it? Yeah, these steps and make you go to the breakout rooms again for 20 minutes to actually parallelize the code snippet yourself. So you have two options here. You can either code it from scratch, or you can take the Python, the pthreads py skeleton that is in the sources. And yeah, you have some hints here, and I will post the other slide here again so you see what steps need to be taken. And then I would also like you to compile and run it. If you have any questions, as always, don't hesitate to come back here. I'll wait for this one person who's typing, whether there's an important question. Why do we need thread handles? This is part of the pthread standards. The function needs the handles to actually work with the threads. So let me show you again. So this is this function takes the thread handles to create the handles afterwards. Okay, so before we get into before we deep dive into those kind of discussions here, I would like you to start with the next exercise, and I will and I will try to get the additional information to you here in the chat. Okay, sound like a plan? Then we're back here at 10:20. Okay, so some had a few struggles with parallelizing the code themselves. So this was, I guess, a good exercise for you to see what pitfalls there are, what different things you do have to think about. I do have a sample solution in the codes, which is the pthpi.c source code, which you can run to actually do the second part of the question, and which hopefully answers all questions you have or that have arisen during your coding in the first part. So that's why I'm not going to go into much of the first question. Instead, I'll want to talk about the second part, namely what happens if you compile it and run it with different numbers of threads and different ends. So n more or less just says how many elements we have to sum up. And this will give us a more precise estimate of pi. And as Johannes correctly pointed out, you have to look at the sizes of your data types, so you don't have to, or you can't use ridiculously high numbers for this. But the ones I gave you here for testing purposes do work. Then what happens if you change the number of threads? Well, you're going to have different rounding errors, different private sums, so everything that happens within the threaded function is going to change. And then what do you see in the output once running it? Well, we already saw with the Hello World program, you're going to have different orders. And also you can see that the printed value of the sums is not always correct. So in the long run, this also means that the estimation of pi is not always correct. So I again have two sample outputs for you. Just running the program twice, once after another, on the same system. This was one run where you get the correct answer for this estimate. On this side, you see the estimation of pi has gone horribly wrong. And this has to do with the accesses to sum. They're not protected. So as you already see here, thread 3 is already printing out the sum before thread 0 has printed it out. So they must have been accessing it at the same time, or at least very close to each other. Everyone has the same value for sum. So also here, this can't be correct. I mean, if you're the first thread using or looking at the global sum and adding your own small MySum part, you can't actually have the same value as the last thread who is adding the nth element. So here's some things that will give us some more food for thought. And those sections where these things can happen are so-called critical sections. Before I go on with that, do you have any more questions on the exercise? I'm kind of rushing now a bit because we took a bit longer for the pi example than I had thought. No one started typing? Okay, so I'll continue. So those sections are called critical sections. Those are exactly those sections that you already came up with at the very beginning. So the question we have to ask ourselves now is, how do I protect access to this? How do I, in the end, sequentialize the access to these sections? Even though we're running in a parallel program, there are going to be parts of the code that need to be sequentialized again. So one method to do that are so-called mutexes. Mutexes ensure mutually exclusive access to a critical section. This is where they get their name from. And they're native to the pthreads library. So again, you have different functions that initialize a mutex, that lock a mutex. So once you lock the mutex, no other thread that wants to access this area can actually access the mutex, lock it in itself, but instead has to wait until it can lock the mutex itself. So the one thread that has locked the mutex can proceed into the critical section, do whatever it wants to do, And after it has done everything everything it needs to do in the critical section, it needs to unlock it again so that other threads can use the mutex and enter the critical section themselves. If you do not unlock it, you're going to end in a deadlock because all other threads are waiting for the mutex and cannot access it at any time. And again, you also have this destruction function to clean up in the end. So looking at our estimation of pi, what steps do we have to take to protect this critical section? Let's look at this critical section again. So it's going to be somewhere here. Think about what you have to do. And I'll give you the answer directly because we do not want to have a next breakout session for this one. Again, you will have to set the mutex as a global variable. You have to initialize the mutex in the main function. You have to identify the code snippet or the code lines which need to be protected. So we've already done that a couple of slides before. As I said, you need to lock the mutex in the thread function before accessing the critical code, and afterwards you have to unlock it again. And in the very end, again, you destroy the mutex. So keeping these steps in mind, again, I will open up this slide afterwards again so you can look at those again. We go into the next breakout session for 15 minutes, where you again can take a skeleton and try to mutex it yourself. If you're running into problems at any point there, ask. And once you get close to the end of the breakout session, feel free to, again, use the solution file, compile and run it just a couple of times, and look at the differences you see to the previous version. So 15 minutes means we're back here at 10:53. Okay, so you hopefully managed to find the critical section and mutexify it. And we already discussed where the critical section is, and that should be on one side, the sum needs to be protected, which also means that you need to protect the print statement with the sum, because once you unlock the mutex, it could happen that another thread adds its own sum to sum before you actually get to printing out this message. Now, when you run it, you will again see that there's still difference in ordering the threads. So you sequentialized the whole thing, but you have not yet ordered it. So it can happen. So you will see if you mutexify it, as I did on the 2 slides before, namely you having your own sum within the critical section and also having the other sum within, you will have it ordered. So you have the statements of rank 0 together as you do with the statements of rank 1, rank 3, and rank 2, but it's not ordered. So it's not that you have rank 0, rank 1, 2, and 3, one after another. If you do want to do that, there's other means you have to take. So what can you do with the mutex and what can't you do? You can serialize the access to a critical section, but you cannot order your access to a critical section. And very important, you can run into a deadlock with mutexes if you don't unlock the mutexes properly. So this is really critical when you use multiple mutexes, because to be honest, if you only use one, you can usually remember to unlock that one. But if this is not everything we want to do, or if everything we can do, what else is there to have access restriction? Because a mutex, of course, it's always very expensive. You lock a whole bunch of information which no one else can access, and maybe you don't want to do that. So pthreads actually also offer so-called read-write locks, which, as I said, is offered by pthreads, so it's part of the interface. There are according functions, and you can access or you can control the access depending on whether the threads want to write or only want to read the information, which can be very interesting once you're using a large array of information and have some kind of producer-consumer kind of scenario. Another thing you can do is use semaphores, which are used for signaling and not so much for locking. I'll talk a bit more about those in the next couple of slides, but they are not part of pthreads. So there's another library you'll have to you'll have to add. Another thing that pthreads offers are so-called condition variables, which is a bit more complex thing, but which can also be used to save resources. And in the end, there's always varias that you can implement yourself, which I think you already did in the MPI lecture beforehand. So this is just kind of an overview so that you've heard about different notions, different things you can do with critical sections. And you can read about all of those things in the links that I've put at the end of the slides. But as I said, I would like to emphasize a bit more on the semaphores because those are actually used quite often and you'll hear about them quite often, and they're often confused with mutexes. But actually they do have a very different, they're there for different things, signaling and locking. And I won't go too deep into those functions because we're not doing a breakout session on that anymore. But instead, I would like to talk about this producer-consumer scenario a bit more, where you have an array which is filled by the producer with different information, and the different consumers are waiting to do something with the contents. Most of the time, they will only want to read it. So they need to know when they can actually read from it, because if you don't lock the whole thing, they could read from it without actually having information to read from. So this is what a mutex would come in. You could lock the whole array, but then you would have all the threads waiting until the whole array is unlocked again. Everything is written in there, and it would just kind of waste resources. So instead, you can use a semaphore where the producer increases the value of the semaphore, and the other threads can read information as long as the value of the semaphore is large enough. Of course, once all information is read from the array, the threads cannot read anything, and they'll wait until the semaphore again has a value greater than 0. And they know there's something I can work on. So this is much more flexible and more dynamic than mutexes are. Another thing you can do with semaphores is the ordering. Of course, you could also order with mutexes, but again, this would be pretty resource consuming and a waste of resources in the end. There are several scenarios where it does make sense to order access to a shared variable. So here I have the matrix multiplication, which is non-commutative, so it does matter in which order you access it. And you could use the value of the semaphore together with the rank of the thread to order this access. So you check the value of the semaphore, see if it has the same value as your rank, and if it does, you enter the critical section, you do your work, and then increment the value once you leave the critical section. This is something that you can do in the optional exercise, the last exercise on the exercise sheet. And again, there's a skeleton for you to use if you do not want to do everything from scratch. And also there's a sample solution in the codes I gave you. So this is everything that I want you to necessarily know after 2 hours of pthreads lecture. I hope you had some fun with the with the hands-on. If there's any open questions on the hands-on or anything else with pthreads, I mean, in 2 hours, I obviously can't cover everything, but I hope you have a good idea of what pthreads do. Most of the time, you'll probably use a more sophisticated interface like OpenMP, but nonetheless, it makes sense to know the basics underlying that. So if you have questions, I hope it's okay for Sven if we just kind of talk about that 2 to 5 minutes. And if not, feel free to write a mail and ask anything there.